Hello, good evening, and welcome to week 4 of the live interactive session of Fundamentals of Micro and Nanofabrication. The course instructor is Professor Susoban Vasti and Professor Sankar Selvaraja from ISC Bangalore. I am the PMRF teaching assistant Vikas Pandey from IIT Jodhpur. This is a brief about me. I am a PhD scholar in space technologies at IIT Jodhpur. I have a background in VLSI and electronics and communication. I work in area of HEMT, sensor IoT, machine learning, microfabrication, and additive manufacturing. These are the class credentials and the YouTube link where you can access all these videos. And these are my contact details. Okay. So in this week, we have covered chemical vapor deposition. So if you have any particular question about it, you can ask anyone. Hello.
Hello, Vikas. Your voice is coming very slow.
Okay. Hello. Am I audible now?
Yeah, better. Yeah.
Okay. So I'll speak louder a bit. Okay. So let's start with the deposition techniques. So till now, we have first seen how doping is done. That is how we are adding some material into the wafer. Okay. Then we saw how we can grow silicon oxide. That is a growth technique. Now we are coming to something where we are depositing something over our wafer. Such technique can also be required for our fabrication process. So, what is a deposition method? Okay, this this has it is CVD. Okay, chemical vapor deposition. Okay, so there are in general two type of deposition technique. There are multiple subtypes inside it, but basically we define the deposition technique into two. One is CVD, that is chemical vapor deposition. The other is PVD, that is physical vapor deposition. So what happens in case of CVD is that reactants in form of gas react on the wafer surface wherever we want to deposit and create a solid material. These are used for high quality semiconductor films like silicon dioxide. That also very high quality silicon dioxide where we are not able to grow, but we want to deposit very high quality silicon dioxide. We will go for CVD. Then there is another process that we will cover in the next week. That is physical vapor deposition, in which the material or the material that we want to be deposited is actually available to us. Like if you want to deposit silicon dioxide, we have silicon dioxide and we will just change the state of it. Like we will evaporate it or create a plasma out of it and then deposit over another material. Again, condense over it. It is more common in case of metals and dielectric deposition where we don't want very good quality ones. Okay. What are the key differences? CVD, it is better film quality, but it has more complexities and used for semiconductor devices. Whereas physical vapor deposition is simpler, much cheaper, and used for non-critical layers. That means that will not actually determine our electrical properties or that may not affect much if their orientation and these are not fixed. Fine. Any questions still here? Anyone? Okay. Yeah. You are able to hear me, right?
Yes, yes, yeah.
Okay. So Whenever we are talking about deposition techniques, there are three things, three key concepts that we are concerned about. One is uniformity, second is conformality, third is step coverage. Uniformity, what it is? It is the consistency of film thickness across the wafer surface. So if we have wafer, we it should not be that here it is 200 nanometer and this side it is 150. That is not uniform, because in that case what will happen that suppose we are creating some device here at different presses we are creating different devices, it will give different characteristics. So we want a uniform thickness, whatever technique we are using, either CVD or PVD, we want a uniform thickness. Second is conformality, the the power or ability of the system to deposit film to uniformly cover the underlying topology. That is, one, one is uniformity, the thickness should be uniform. And conformal means it should cover all the areas. It should not be that in one area it is good, other area it is not. Okay. A good conformal coverage is uniform thickness over all the features. And poor conformal coverage is thinning or sharpening. Like if suppose you have some structures that are already present, some source, drain, and all thing, and when you are depositing, if it is depositing uniformly across this source, drain, all like I will make it a big. Like suppose that we have a structure like this made up of metal, and now we want to deposit something over it. So if it is giving us uniform thickness throughout, then it is conformal. But it might happen that it is depositing good here, but in these parts it is very thin or it is not getting deposited on these corners. This corner it is deposited, but this corner it is not deposited. In this case, it will be called as a poor conformal coverage. Okay. Third is step coverage, a measure of how well the film thickness covers the steps and trenches of the wafer. That when we are like seeing the side view, we will see that there can be some structures like this, okay, and then maybe some deposition over it. So when we are depositing, it should not. Let me put some other color. Suppose that we are depositing something over it. So if it has a good step coverage, it should be deposited here as well as here, like that, a uniform step coverage. Whereas if it is getting deposited something like here it is deposited, here it is very thin, then it is getting deposited here, and it is not getting deposited here. That will be a poor step coverage. Okay. So in this week, we have mostly discussed about CVD, that is chemical vapor deposition. So what is CVD? From the name itself, you can understand that it utilizes chemical vapor, chemical reactions to deposit materials onto a substrate. So if we talk about a basic CVD, it will look like a tube, simple, a very simple CVD. It will look like a tube. Generally, since it has to go to some higher temperature, so it will be a quartz tube. And in this, there will be an inlet, an outlet, and then here we will keep our wafer on which we want to deposit. And there are two ways that you can insert the reactants or precursor, it is said, either mixing with the gas or you keep them here. And this whole thing is getting heated. This is a very simple CVD I am talking about. So what it will be, eh, like whenever the airflow will be there, and this since it is heated, it will come with gas, and the reaction is supposed to take. So there might be that in this part there is another temperature, this part another temperature, and the optimal temperature at which this reaction, suppose we are taking two different materials that will react. Okay, so that reaction will take place here, and it will deposit over these wafers, and the byproducts will flow out along with the gases. This is a very simple CVD method. Then there are different things associated with it. So, so what are the components that we have in a CVD system? Which is important is a chamber. Why chamber? Because these reactions cannot take place in an open environment. We want to have a controlled environment where these reactions take place. So that is the chamber. If if we talk about the chamber, in this case is the quartz tube we are talking saying. Second is energy source. Here I was saying that we might have heaters. Okay. There can be some other energy source also, like heat or thermal energy is one. Second one is RF, radio frequency or radiative energy. All such energies which facilitate the reaction. Third is precursor, that is the starting material or the chemical reactants that we have. Okay. Then the substrate on which we will deposit. We have talked about substrate in details in week 1 and 2. Not 2, I think 1 and starting of 2, right? So this is the substrate, this is the surface on which this deposition will take place. And the last one is the susceptor, that is the mechanical support. Certainly these wafers I draw like they are standing there, but they cannot directly stand there. They will have to be put over some support, that is the susceptor. What are the applications that CVD is used for? It is used for high quality thin films, especially used in semiconductor fabrication. Second is epitaxial growth. This is a very important application, and this is something that will grow further in subsequent years. Okay, where the crystal, like whatever wafer we have, we want another material to have the same crystallinity as the one below. So if we have a silicon wafer and then over it we are depositing some material, so we want it to have an aligned crystal with silicon. Then over it, suppose that we want to deposit something else, again we will try to align. So a single depositing, and that also uh, matching the crystallinity with the substrate below. That epitaxy growth, this is a very important application. The second one, the third is heterojunctions, like silicon and germanium and gallium nitride. Okay, where this it is very much like epitaxy only, but where these two materials will have slightly different, uh, like slight mismatch at the border and at the boundary, and that will create something known as heterojunctions, where a ample amount of electrons are produced, and nowadays based on that like high electron mobility transistors and these things are being made out of this. So these are two important applications, as well as they are commonly used in semiconductor fabrication and sensors too. Okay, so what are the advantages associated with CVD system and what are the disadvantages? First advantage is its quality of film, very low contamination and high uniformity, since we are creating the material there itself. We are not bringing it from anywhere else. So we can control the contamination level, and that will give us very good coverage also, since uh, all the whole wafer is actually exposed to the reaction. So it is quite uniformal as well as low contamination. Second is we can make a wide material range because as we want to deposit something, if there is some chemical reaction that can facilitate the like formation of that material, that can be done. Okay, so in as such, a wide range of materials can be made. Then conformal coverage, because again I said it is gas, like most precursor are in form of gas, so a good coverage is also possible. And one very important thing is that whenever we are talking about semiconductor fabrication, many processes require very high vacuum. And to create vacuum, it might seem like what is the problem with creating vacuum? Uh, for a simple system, simple PVD system, I will just give a reference that like sputtering or this thermal evaporation, it takes hours, like 4 or 5 hours to create good quality of vacuum. Okay, sometimes even 8 hours if we are going for very good quality vacuum. Okay, as such, if you are operating at low pressures, like this whole process can be done at uh, very small, like very normal process, not very high vacuum is required. Simply you can clean it by sucking out the air, and then next you can start the deposition. As such, it it is less costlier because less time, as well as you don't have to wait for different process, like one process, after that you can go for another process. The disadvantage is very high cost because precursors are there, the equipment and operational complexity, like you are not controlling things, the whole chamber has to have the reactants and all. Second is high temperature. So if it is high temperature, we said about wide material range, but at high temperature, some materials like plastics and flexible electronic materials, they will melt. So it is not applicable for those. Then there are not many parameters that we can control while doing this method. Like you can control the temperature, you can control the pressure, gas flow, but not other things. Like when we will talk about physical vapor deposition, we can even tune the power, how much power is being used, how much, what will be the rate of deposition and these things. Whereas in this case, it will somewhat reaction dependent as well as pressure and temperature dependent. That will determine the limit, like that will determine the control parameters. These are some of the disadvantages. Any questions still here? Hello. Yeah, you can unmute and speak. Anyone?
No, Vikas, no, it's clear.
Okay, fine. So, what are the essential components in CVD system? We have seen, but now we are properly going deep into the CVD system. So, as we talked about, first is precursor. So, what a precursor should be? It should be volatile and thermally stable because we are uh, going to operate at high temperature. Third is it should be decomposing cleanly. That means it should not have some like after reaction, some part unreacted should not remain there. Okay, it should properly disintegrate at the temperature we want, as well as it should not be very uh, like some materials are there that will have the particular reaction at one single parameter only. No other parameter will actually facilitate the reaction. That is not a good precursor because we want to we may want to vary our thickness, we may want to vary our this the uniformity and these things. And for that, we want to have some wide deposition window so that we can have some control over it. Okay. Third is, it's it is not that the reaction happens and after that it actually creates some blast and all that, as well as it comes in the atmosphere and everyone gets fainted and this thing. It should not be like that. And if it is something like that, it must be having like there must be proper way that we can control it as well as treat it and then remove it. It should not be that we cannot later on control what is coming out. Second is the substrate. Like uh, we are commonly talking about silicon. Okay, it must withstand high temperature and remain non-contaminating. That means it should not be that the substrate itself is actually going to create some reaction, like it is disintegrating into some different material, and whatever we wanted to deposit, it got deposited, but actually the substrate itself created some third material that we don't want. Okay, so that should not happen. So that is why we cannot go for things like glass. Normal glass, if you go for CVD, what will happen? There can be some like soda lime glass, if we are talking about. There can be some contaminant, or it will actually uh, melt at that temperature, 1000 or 1100. Like it will melt. That is why silicon, quartz, and sometimes steel is even used when we are not going for very high temperature process, like 300, 400 degree, we can go for steel. Third is susceptor. Again, this is very important that it should not take part. Susceptor has only one role, that is physical support. So it should remain rigid throughout the reaction, like whatever temperature it reach, it should not be participating in the any kind of reaction. It should not changing its form, like it should remain solid whatever form it was given. As such, things like graphite, quartz, silicon carbide, and sometimes even alumina is used in normal cases. Alumina, like alumina boat, and these things are also used as susceptor. Then is energy source, and that defines the type of CVD we are talking about. Okay, it is very important because reactions will not take place on their own. They will need some activation energy, and to provide the necessary activation energy for the chemical reaction, we have to give some energy, and that energy can be through thermal heating like nichrome coils, even IR, or RF induction. In case of RF induction, we are talking about plasma and all, where we are creating plasma, and due to the ions we are giving the energy. Sometimes combination of these are also used, like heat as well as plasma. There are different methods that can be used. Now, the most important thing is precursor. What are the consideration? First one is volatility, that is preferably gaseous or easily vaporizable. It should not remain solid for long, like it should not remain solid at the temperature we want. Suppose that we have a quartz tube, and the reaction will take place at, say, in the central area. We are putting our wafer on susceptors, and here we are putting our precursor. Okay, and the reaction is supposed to take place as, say, 850 degrees Celsius. Okay, so what should be the preferred temperature at which these are solid materials, let's say, and we want to vaporize it, and we are putting some gases in. So can anyone tell what will be the preferred temperature that we can go for? Like if the material is vaporizing at that temperature, it will be fine. Anyone? Just answer this much, that it should be more than 850 or less than 850.
It is vaporizing at 850, right?
No, the reaction is taking place at 850, the actual reaction we want. So the evaporation should take place at lower temperature or higher temperature?
It should happen at lower temperature.
Lower temperature. And why so?
Otherwise, it will not be in vapor form.
Yes, so it will not be in vapor form. And if we are, even if we are, suppose that it is vaporizing at 1000 degrees Celsius, then what will happen that this area, we will have to go to 1000 degrees Celsius. And as such, we will not remain at 850 degrees Celsius. In this area, the reactant itself will be at a higher temperature, and the optimal conditions we will not get. So it is better to have a low, maybe 200 or 300 degrees Celsius, at which it will vaporize, or even lower than that. Or it should be in the form of gas, so we can directly put the gaseous form. Okay, that is the first uh, preference of any precursor. That is why we cannot take any material as the precursor. There should be some limitation. Okay. Second is thermal stability. It should only react under the controlled condition. It should not react somewhere beforehand only. We want the reaction to take place at the specified zone we have defined. Then we don't want any unwanted byproducts or side reactions, because suppose that we want to deposit MOS2, and along with that, on it, it is also creating SiO2. So it will not serve our purpose. It will have a mixture of MOS2 and SiO2. We are not interested in that. We are interested in MOS2 only. Okay. So all other byproducts should be in gaseous form, and it should come out. That is also an important consideration when we are talking about the precursor. Then availability and cost. It should not be very costly, as well as it should not be a like rare element that we have to bring it from Mars and then only we can use it. Such a material is of no use. Okay. Then safety concern is also there. It should not. It should be non-toxic, preferably. And if it is toxic, that toxicity and everything should be properly known, and precaution should be taken beforehand only. Okay. And non-proliferate. That means it should not like come out of the reaction chamber. It should be properly contained inside the uh, reaction chamber only. But these are some things that actually don't happen. This safety concern is something in this process that is mostly compromised. And that is why other safety concerns are there. Like it has to be properly covered, multiple layers are put over it, as well as it should be in another chamber, like whole thing should be in another chamber where such contamination should be covered. Whoever is handling should be handling it with proper mask, gloves, and all. Okay. And what are the available precursors that we have? There are a lot of materials that are available. If you just go to the one of the most common, or we can say the most preferred chemical vendor, that is Sigma Aldrich, there are over 220 precursors for various elements that you can find. So in a sense, you can, and mixing them in different proportions will give you again different materials. So there is a availability of lot of materials, lot of precursors for different materials. So now next is, yes, any questions still here? Yes. Anyone? Okay. So moving to overview of this mechan what is the mechanism behind the CVD? So what are the key processes that happens in CVD? Is the first is gas flow. That is one important thing because there, if we are talking about CVD, first we are talking about gas flow is there. Okay, how this gas flow stream will be there, that is important. It should not be that this gas is flowing very fast and it is not actually stopping at the boundary condition. That is where the reaction will take place. Or it should not be so slow that actually it is remaining there even after the reaction. So it should be controlled. Second is diffusion to the surface. The precursor that is being carried by this gas or the gas itself can be a precursor must diffuse through the boundary layer to reach the wafer. That is, at the interface, some deposition is taking place, and that diffusion, after the deposition, like we saw in case of silicon dioxide growth, there will be diffusion of the materials towards the boundary where the deposition will take place. Actually, these things don't take place on the top surface generally. They will go till the interface. Okay, and that is the primary mechanism through which this reaction takes place and CVD deposition takes place. Third is surface adsorption and reaction. The precursor molecules, whatever we want, should actually go and adhere to the surface for the reaction to take place. They should sit on the surface for this reaction to take place. It should not be that they are not actually adsorbing on the surface. And the second thing is that the chemical reaction should actually take place for the film to be formed, as well as the byproduct or of the reaction diffuses back. Like if it has formed the layer at the bottom, like at the interface. After this, whatever the byproduct, say hydrogen sulfide, or whatever is forming, that should come out and go. It should not get trapped inside. Okay. What is a bond? When we are talking about this, we were talking about boundary layer. Okay. So what is the boundary layer and what is its role? So it is due to the non-slip boundary condition near the wafer and susceptor. So that is, we have the susceptor that is holding the wafer. Okay, these are the boundary condition. That means the reaction that is taking place. Whenever we talk in terms of equations and all, we are talking at the place where the specific reaction will take place and these things. That is happening near the susceptor. We are not having the same condition throughout the chamber. We want the condition near the wafer. So certainly, if near the wafer, it will be near the susceptor also. Then, sorry, just a minute. Yeah. Oh, am I audible now? Hello. Yes. Anyone? Can anyone respond? That am I audible? Hello.
Can you repeat?
Yeah. Am I audible?
Yeah, yeah, you're audible. Yeah.
Okay. Okay. So this this boundary layer thickness, that delta, is proportional to actually the Reynolds number. It is inversely proportional to square root of Reynolds number. So what is this Reynolds number and why is it significant? That is, if we talk about the flow in the CVD reactor, the flow will be of three types. Any flow can be of three types. Molecular flow, that is very low density, no collision of molecules. So it is like very smooth flow, and this typically happens in vacuum. That means very low density of gas molecules are there and they are flowing freely without any collision. This is molecular flow. Second one is the laminar flow, that is streamlined flow, and this occurs at low Reynolds number, and this is the preferred flow that we want in case of CVD. That is a streamlined flow, simple flow, one molecule following the other in a streamlined fashion. Third is turbulent flow, that is chaotic, that in which a lot of collision and unpredictability is there. So this actually laminar flow, how laminar the flow is, that will actually determine the thickness of the thickness of the layer that we are depositing. Okay, so what is the Reynolds number? It is a dimensionless number indicating the flow region. So the formula is generally in terms of the density of the gas molecule, velocity of the gas molecule, diameter of the flow we are diameter of the pipe or the tube that we are talking about, mu, that is the viscosity of the material, and that will determine Re, that is the Reynolds number. And for a laminar flow, this Reynolds number should be less than 2000. But if it is very, very low, it will again be a molecular flow, like very slow flow, that will become like a molecular flow. And if it is above 2000, it will be a turbulent flow, and we want the flow to be a laminar flow. So when designing the CVD reactor, we have to maintain laminar flow to ensure uniform deposition and predictable growth rate. If it is a turbulent one, we will not be able to determine the growth rate every time. Like suppose that I am doing it today, next it is giving me 300 nanometer deposition, next day it might give 50, next another day it might give me 400 if it is turbulent. So when designing this CVD reactor itself, it has to be taken care that the flow should be laminar. So inlet and outlet, everything should be clear. Sometimes it even happens that we have everything made, but the flow is not laminar because the outlet is covered. Like we have one outlet, one inlet. Okay, so inlet is fine, but outlet there is some clogging, or the complete flow is not there, or maybe that the uh, inlet is too big, or we are giving a lot of air in, but the outlet is small and it is not getting out easily. So these factors we have to check care every time before deposition. Everything had to be checked, cleaned, and this. Okay. So how do we ensure that this flow is uniform and every time we are maintaining the same flow? This is done using mass flow controller and pressure regulators. Mass flow controllers are, I have not put an image, are simple devices like this size, small size, where we have an inlet, outlet, and we put the flow rate that we want according to gas. Like if I am flowing hydrogen, I will put hydrogen 30 SCCM. SCCM is the standard cubic centimeter per minute. Cubic centimeter per minute. So in 1 minute, how much volume of gas will flow, that we determine using MFC or mass flow controller. Okay, they are very much like they are electrical devices. electromechanical, we can say, where they control the flow rate, and precise flow rate are maintained throughout the process so that we get a laminar flow. We don't get a turbulent flow, as well as these tubes, inlet, outlet, everything is clean. Then, based on the temperature also, there will be two regimes of growth. One is reaction rate limited, the second one is mass transport limited. The reaction rate limited when the surface reaction is at the bottleneck. Okay, it will exponentially depend on temperature. Surface is readily available. Uh, we don't have an issue of reaction sites, we can say. In this case, temperature will be the determining factor, and the rate will be exponentially limited to related to the temperature. Any small change in the temperature will lead to change in the growth rate, and this is typically the first part of reaction or starting of the growth we are talking about. The second one is mass transport limited, when the diffusion through boundary layer is the bottleneck, where wafer is there, some growth has already taken over it, let's say like this. Okay, now how much material is diffusing in to the surface for the further reaction, that diffusion will determine the output, like how fast it is growing or growth rate. It is linearly dependent on pressure, and temperature is having less dependence. So slight changes in temperature will not have much effect when we are getting into mass transport region. Okay, so it is P total, that is the total partial pressure, by delta, that is the pressure that we are talking about. Okay, so while designing the reactors, the CVD reactor, this gas flow dynamics are very important to control the boundary layer and achieve a uniform deposition. Okay, how the transition between the, we have talked about different regimes, like it is temperature control, then it becomes mass flow control. Okay, so how the transition between these two regimes take place? When at low temperature, typically reactions are typically it is reaction rate limited, and reaction rate will actually depend on the present temperature. When at high temperature, it is uh, transition to mass transport limited, as well as the impact of the gas flow is there. Increasing the gas flow velocity can transition it from mass transport to reaction rate limited. Like if it is having like a lot of readily available precursors are there, all the all the molecules are readily available at the interface, at the boundary position, then it will become again uh, it will again become the reaction rate limited. Whereas if we are decreasing the gas flow, that means the precursors will not easily reach. In that case, it will become reaction rate limited. What is the strategy to, we have talked about that whenever we are talking about deposition, uniform growth is one very important uh, thing that we are talking about. That is, uh, for uniform growth rate, we have to increase flow velocity. This will reduce the boundary layer thickness, and that will improve deposition. So it will, the molecules or the materials that we want, that will be easily available for the reaction. Then second one, and this is one very important thing that people play with or tune with, is the wafer loading angle. Wherever I showed, I didn't show that wafers are kept like this. I generally showed that they are being kept like this. The angle that we are keeping, like if it is vertical, the reactants might not get absorbed over it. Okay, And it is not that at one particular angle we will, uh, like at all angles we will get the same thing. At one particular angle we will get one growth rate. That means at different angles, by changing the angle we are keeping these wafers, that will determine the growth, how uniform it is, as well as what is the thickness that we are getting. So how this, what these reactors look like or how they are made, they are basically classified as two, that is hot wall reactor and cold wall reactor. In case of hot wall reactor, there is chamber heating. So whatever one I was talking about, that is a hot wall reactor where the whole chamber or the quartz tube is heated using resistance heaters. In this case, the thermal mass will be very high due to entire chamber being heated. The temperature is very high, and that is why we cannot say that like this. Suppose that we have heated this much, this area of the chamber at 700 degrees Celsius. So we cannot say that this is 680, this is 710, not like that. Since it is at very high temperature, due to uh, such high temperature, actually there will be conduction and radiation, and everything will almost become uniform. But it has high precursor consumption. Since the whole chamber is heated, every a lot of reaction will actually take place, and it will not get deposited. It might flow with the air itself, the gas we are putting in. But we want that maximum deposition should take place and maximum reaction should take place on the wafer. But since the whole area is heated, we cannot stop the consumption of precursor. So reaction can occur at any place on the chamber wall, even leading, like I said, that there can be some blockage, and this blockage can actually happen due to deposition on the wall as well as in the tube itself. Going out also, the reaction, the reactants after reacting, the products actually reach there and they might deposit there. And since uh, this is a gas phase reaction, the deposition rate is not very high. Deposition will take place, but it will not be very high. It is generally used in LPCVD. We will talk about LPCVD just after 1 2 slides. Okay. It is very common in case of LPCVD or low pressure CVDs. Whereas there can be another CVD reactors which are cold wall reactors or cold wall reactors, in which only the wafer where the actual reaction has to take place is heated and the chamber walls remain cool. This is for low thermal mass. This will actually result in low thermal mass, more uniform, since only the area that we want the reaction to take place, that is heated, and that is at the point where we want the reaction to take place. That is at the condition where the reaction will take place. But there is one problem, that it might not be very uniform. The, the temperature, since like in this case we were talking, the whole area is getting heated. So there will be some, like if you say that some small part is not heated, that is not possible because it is at high temperature. Whereas in this case, a small area is only getting heated. So there will be losses and all. And as such, the temperature cannot be uniform, may not be uniform, because some area might be leading to radiation losses from the wafer. But the precursor consumption will be low, as only the area, the molecules or the reactants that will reach the wafer will actually take part in reaction. Other area, there will be no reaction since they are not heated. There will be minor reactions. These are the reaction rate is typically high because only the area where we want there the reaction is taking place. It is common in APCVD or atmospheric pressure CVD for process that require rapid temperature changes because in this case the cooling will take in normal or LPCVD the cooling will take a lot of time as well as temperature changes steps and all that is taking time. In case of APCVD where uh, we want the temperature to change rapidly, one temperature then shift to another temperature. For that, wafer heating is a better option compared to heating the whole area. So, what is the difference between this APCVD and LPCVD? AP means atmospheric pressure and LP means low pressure. APCVD works at atmospheric pressure or slightly higher pressure. That means it will have uh, the same pressure as the one outside. It has higher growth rate due to mass transport limitation because reaction rate is not limited by the temperature. We are maintaining the temperature at the wafer itself as well as whatever precursor reaches there that will get reacted. It is not that it might not get reacted and it might flow. It is not that common. When we are talking about temperature uniformity, it is not critical since we are talking about a mass transport limited reaction. The temperature uniformity dependence is weak. So, as I said that in case of this only hitting the wafer and all, in that case the temperature variation can be there on the wafer somewhat, but that is not the limiting factor for the growth. But what is the limiting factor? That is the gas flow dynamics. How the gas is flowing, that is very important. In this case, the advantage is that the reactor is small, cold wall, and used for thick, fast deposition. In case where we want thicker deposition and fast, we can go for APCVD. In this case, it is commonly used for dielectric deposition and thick film deposition. Whereas if we are talking about low pressure CVD, LPCVD, they generally operate at low pressure but not vacuum. We are not talking about vacuum. We are talking about simply low pressure. That is where we are lowering the pressure, removing some air, but it is not in vacuum. Okay, the growth rate is slightly lower than APCVD, but not like very low. It is simply a bit lower than APCVD. Temperature is very important here since it is temperature controlled, temperature limited. So any variation in temperature, even 5-10 degree, it will lead to some changes in the growth rate and the growth. Gas flow, that is less critical because everything is actually getting reacted due to the high temperature. In this case, but the reactor design is typically complex, hot walled, and high quality deposition can be done. Uniform thin films and semiconductors, they are done at LPCVD. Okay. Any questions still here? Yes, anyone? You are able to hear me, right? Hello. Yes, anyone? Maya Manoj or Hari Prasad, are you there? Hello.
Yes, yeah.
Yeah. Are you able to hear me?
Yes,
Oh,
yes,
fine.
sir. Yes, sir.
Okay. Okay. Yeah. Next is we have talked about this about the gas flow as well as temperature. Then there can be another effect, that is pressure, because we talked about LPCVD and APCVD. In both, we are talking about pressure, low pressure and atmospheric pressure, right? So, what is the impact of this pressure on the growth rate? Reducing pressure from 1000 millibar, that is generally the atmospheric pressure, 1333 we say, but around 1000 millibar. Reducing it to 1 millibar, that takes place in case of LPCVD, low pressure CVD. Okay, gas flow velocity. This is actually when we have a low pressure, like we are taking out the gas fast, we are reducing the pressure. Okay, outlet. If this is the outlet and we have put a pump and we are taking out the gas, so the inlet gas, whatever is coming, that velocity will increase because there is low pressure and it is sucking out the gas. As such, the diffusion coefficient, that is D, that will increase significantly due to the low pressure. The, the rate at which this diffusion was taking place, that will increase. And that also, we are saying that we are reducing this pressure by 1000 times, so that will increase by 1000 times. The boundary layer thickness, that is delta, that is the whole thing that will occur, like the whole part that it has to cover, will increase, but overall diffusion is enhanced. Okay, D is enhanced, so even if the boundary thickness is increasing, there will be overall increase of say 300 or something. Okay, so although the pressure decreases 1000 times, the growth rate only increases by 3x or something due to the diffusion, because one is increasing, the other, like one is cancelling out the effect of another. As such, in case of LPCVD, larger temperature range for surface reaction rate limited growth is required. For the temperature sensitivity, LPCVD growth rate becomes highly sensitive to temperature, requiring uniform heating. Okay. So, what are the challenges in CVD reactor design? One is, like, there are three parameters that we take in account when designing the CVD reactor. That is, one is mass depletion. The problem is that the precursor concentration will decrease as the gas flows from one end of chamber to other. Like reactions are taking place and somewhat the precursor is getting consumed and all. And when we are going towards the end of the chamber, like in the direction of flow of the gas, the precursor concentration will be lower. And as such, it can cause non-uniform deposition across the wafer, especially in case of APCVD where the pressure is not getting lowered, like it is not getting, getting sucked out. Okay, so as such, so if we have some wafers like this, so this one will, whatever deposition it is getting, it might be higher than the deposition at the last. So if it is in the direction of flow. Okay, so what is the solution for this? This is that to compensate for this, some excess precursors are flowed, like more than required, but this will actually lead to some increased cost. Second problem is axial diffusion in case of LPCVD. Okay, Just- So the problem is that the gas flow between closely stacked wafers. So if you are not keeping adequate space between the wafer, so the gas flow from one wafer to another wafer and so on will be limited, leading to pressure like different pressure available. And on the first wafer, the pressure will be different. Second wafer, the pressure will be different. Third, pressure will be different. So as such, it will actually lead to non-uniform deposition again. So we cannot determine in which case what deposition will be there. The solution is to design the wafer stacking such that there is sufficient space for the gas flow as well as the pressure is uniform. Next is there should be some real world consideration. Like we have to take care of the fluid dynamics, okay, and that is done by making some simulation and along with that some experience is also required. People doing working in this field will actually understand that okay, if we do this, this will happen and such things. Okay, so the focus area while designing the CVD reactor is that we ensure uniform temperature in LPCVD, and in case of APCVD, we focus on managing the boundary layer, that is the diffusion dependence. Okay, so what are the surface reactions that occurs in case of CVD? So there can be some common type of surface reaction that occurs in CVD. One common thing is pyrolysis, that is the decomposition of precursor due to the heat. Like in case of silane, this is a common precursor used to deposit silicon, and it is poisonous, so it has to be handled with care. Okay, it is where the precursor will decompose at the specific temperature. Okay, the thing is that for such reactions, low temperature is required, and the precursors are a bit unstable, used for elements like silicon, aluminum, and titanium. Second type of reaction that can take place in CVD is reduction. Okay, where hydrogen. So along with this, whatever material precursor we are given, one another thing has to be added, that is hydrogen. So hydrogen will reduce the precursor, like silicon chloride along with hydrogen that will give silicon HCl. But here the problem is that stoichiometry cannot be maintained easily, since the proportion of mixing of hydrogen, availability of hydrogen and saline, that is not uniform. Hydrogen is gaseous, silicon chloride is solid, and then we are mixing like that is flowing together. So that can be a problem. So commonly used for silicon, tungsten, and aluminum. Then in some cases, oxidation, where we are giving oxygen along with the gas gas flow. In the gas flow, we are putting oxygen, like silicon hydride with oxygen that will give SiO2. This is often used for silicon oxide Uh, formation. There are some other reactions also, like nitrides, where ammonia is used, carbides, where CH4 is used, or there can be some materials where disproportionation can be there, where the same material, no other precursor, it is broken into two materials, like germanium and germanium Gi2. Okay, that is vinegar. So such reactions can be there, and based on these reactions, the CVD will work. Now, as we talked about CVD, one important application is the epitaxy. Any questions still here? Yes. Anyone? Okay. So, what are the parameters uh, for optimal epitaxial growth? First one is high temperature. That will, when we are talking about epitaxy, that is with the method of CVD, generally LPCVD or more commonly called as MOCVD. Okay. This this epitaxy will be used to deposit something in the uh, some crystalline material in the same having the same crystallinity as the substrate. So like we are depositing something, uh, you can think of it as like we have a building, okay, and then we have to over it we have to make another building, and that also perfectly aligned over it. There should be no, like, there should be minimal deviation. That is somewhat you can understand as the epitaxy. Okay. Key fact What are the key factors that will determine the epitaxy? That is, first one is high temperature. This high temperature will enhance the surface diffusion, allowing the nucleus to reorganize and align with the substrate. This is very important that the nucleus that we are, the nuclei or the react, output reactant that we have, that has to reorganize and align with the substrate, and that will actually promote crystallinity. Example is silicon epitaxy. This is typically performed at very high temperature for very good quality. Second one is lower supersaturation, a lower partial pressure of precursor. So like the normal CVD, we cannot pump a lot of precursor in. We have to, like, a small amount of precursor. So it will be a very slow process, we can say. Okay. This reduces the nucleation rate, allowing time for proper orientation and growth of large uniform grains. So in a sense, we are putting small amount of precursor, very small amount. It does the reaction, and then we are giving adequate time at higher temperature for it to align to the crystal that is actually beneath it. Okay. So what is the trade-off that we are doing in case of epitaxy? That is slower growth rate due to need for precise control. Here we want to control the thickness, the crystallinity, everything. So it will be a very slow process. In general, it is a two-step CVD process where at low temperature initially the nucleation is done. That is the formation of our next nucleus or the output that we want, the film that we want. And then high temperature growth that will actually let it align with the substrate crystal. Okay. So epitaxy requires balancing nucleation and growth rate to achieve smooth crystalline film with very minimal defects. Okay. Then there is something called known as hydrogen desorption in epitaxy. So common when we are like depositing the silicon, um, we are talking about silicon epitaxy. That is silicon over silicon or any other material. Okay. So common precursors are silane, that is silicon hydride, dichlorosilane, again it has along with silicon chloride it has hydrogen, and disilane, that is Si2H4. They all contain hydrogen, and the problem is that it creates strong bond. Like silicon and hydrogen create a silicon and hydrogen create a strong bond at the silicon surface, and as such, the surface on the top is passive. It is not available for reaction. And then to add more silicon atom and grow the epitaxy layer, these bonds have to be broken. If there is hydrogen present there, we have to remove that. And as such, that hydrogen has to be dissolved. Okay. So this hydrogen desorption is some mostly the limiting, like rate limiting step in silicon epitaxy at lower temperatures. The availability of open site or the dangling board where new silicon atom, like we have silicon, 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 silicon. This is the top surface, okay? Below it we have again silicon, everything. So as such, if we have some dangling bond on the top, then silicon, another silicon can attach over it and we can achieve epitaxy. But if it is bonded with hydrogen, we have to first remove this hydrogen, dissolve it, and that is a bottleneck at lower temperature or moderate temperatures, we can say. And having hydrogen, like ample amount of hydrogen in this, like having high partial pressure of hydrogen, that will actually let the hydrogen to attach to these dangling bonds. And instead of silicon, hydrogen will attach there. And that is one of the limiting factors when using like hydrogen based precursors in case of silicon epitaxy. Then there is second thing, that is how the hydrogen determines the growth rate, like affects the growth rate. Having higher hydrogen partial pressure leads to fewer open sites. We have seen that it will occupy some of the dangling bonds, and as such, the growth rate will be lower. So initially, the uh, if we plot it like time and growth rate. So initially, as the as silane is came being pumped in or released in the chamber, the growth rate will increase. Okay. When the silane has reached some higher pressure, it will it will become self-limiting. It will almost become constant or slowly slow down because of the sorry, yeah. So it will saturate the growth rate and slow down eventually due to the hydrogen saturation of the open sites. If you to compensate this or to overcome this, generally silane is used along with nitrogen atmosphere, where it is mixed with nitrogen. And nitrogen being an inert gas does not passivate the surface like hydrogen. And as such, this mixing silane with nitrogen for silicon epitaxy significantly increases the growth rate due to more available open site. Hydrogen is not that readily available to cover those dangling bonds. But what are the practical considerations when we are mixing the hydrogen and nitrogen? If we are going for hydrogen dilution, slower rate, slower rate of growth, but better epitaxy because there is less likelihood of polycrystalline growth. Whereas if we are using nitrogen dilution, in this case, the growth rate will be higher, but the epitaxy quality can be a bit lower. Then there is another, uh, this is for the silicon epitaxy. Then when we are talking about silicon epitaxy, there can also be a way of, there can also be selective epitaxial growth, where growth is achieved only on the exposed silicon area and not on silicon dioxide. So we are using silicon dioxide as a mask where we don't want the silicon to grow. Uh, How it works? It works by manipulating the desorption and adsorption rate, often by using specific precursor and etchants. So what are the different type of CVD equipments and the related processes? So we can generally say that we have seen APCVD, LPCVD. Okay. Now, when we are talking about epitaxy, they are mostly MOCVD, that is metal organic CVD, where metal organic precursors are used. They have they are a safer alternative with lower vapor pressure, but in this case, carbon contamination is a common problem. These are widely used in materials like aluminum gallium arsenide with precursors like trimethyl aluminum. Even it is used in GaN and LGaN. The common method is MOCVD. Then there are some special techniques like plasma enhanced CVD and laser CVD, where it is like a thermal CVD or normal APCVD, LPCVD, any CVD you go for. But along with the temperature, plasma is used, and plasma will in further lower the activation energy. As such, the reaction can take place or the deposition can take place at a lower temperature itself. Another way is laser CVD, where also laser radiation for the is used for higher growth rate. These are for specifically for wire growth, like nanowires, and these growths are done using laser CVD. Okay, till here any questions, or we should move to problems? Yes.
So like previous one, which CVD is commonly used in labs, sir, R&D labs, like in industry and all.
The most common one is APCVD, okay,
Okay, sir.
and then people go for LPCVD. MOCVD is quite costly and like it needs a lot of setup. Yes, yes, and you are asking something more.
No, no, sir. Okay, okay,
Yeah,
sir.
yeah, and sometimes MOCVD I think is very limited, especially if we talk about in India, we have very limited number of MOCVD. APCVD you will very commonly found. LPCVD also you can find. In IITs mostly LPCVD is also there. MOCVD, ISC have MOCVD. I'm not sure MOCVD or MBE is there. Okay. And then there is one more kind of thing, atomic layer deposition, ALD. That is also a CVD type. Okay. This is also commonly available at many places. Not very common, but it is a costly instrument. So this like the most common one if you go for APCVD, and second is LPCVD. We at our lab we have APCVD, LPCVD, and ALD. And here in IIT Jodhpur, mostly we have APCVD is very common. LPCVD we have, and I think other 1 2 labs also have. These are common. MOCVD is a bit big, and as well as it requires a lot of other things to run it. Actually, it is It is not just that you have a system and you run it individually. It has to be supported by many other systems. Like you have to have the constant supply of gases, as well as whatever output is coming byproduct that has to be properly like neutralized and then disposed of. Everything has to be there. Then only you can have these material, these systems. Yes. Any other questions?
So yeah, you told that I don't understand and not I don't know. I'm asking. So you said for epitaxial growth, right?
Yes.
Previous slide. So in that one, like in point of APCVD, you explained sir, like with any CVD, if you use, what are the problems you're facing and all you said, right?
See,
The pre.
APCVD is a simple CVD method where reaction is taking place, and due to the reaction, some deposition is happening over it, over the wafer. But when we want epitaxy, that is the material that we want to deposit, that has to have the same crystal orientation as the wafer, then the things become complex. Okay, that and that cannot be done in case of APCVD or LPCVD. When we were talking about this epitaxy, na, we are mostly talking about MBE, molecular beam epitaxy, or MOCVD. Okay, this epitaxy is generally done in MBE or MOCVD. It is not done in case of APCVD. It is not a method. It is like an advanced form of CVD process, you can say. And this is not possible in case of PVD. Like when we will discuss about physical vapor deposition, where we already have some material and we are depositing it over a wafer simply by changing the phase, like evaporating it or like hitting it with some molecule and then depositing it. In that case, it is not possible. When we are talking about chemical reaction, only in this case, the alignment of molecules with the underlying crystal is possible. Getting my point?
Yes, sir. Yes, sir.
Okay. Yeah. Any other questions? Yes. Anyone? So let's solve some questions related to this. So in CVD, the following two fluxes are in CV: diffusion through wafer and reaction at wafer or gas interface, diffusion through gas and reaction at wafer or gas interface, diffusion through gas and diffusion through wafer, or diffusion through gas and drift through. Okay, anyway, leave it. Yeah, let's remove this option. I think that second part is missing. Yeah, so anyone with the answers? Yes, any answers for this?
B, sir. B.
B, that is diffusion through gas and reaction at wafer or gas interface. As we have seen that this is very similar to the growth we were talking about, oxidation growth and all, where the reactants diffuse and reach the wafer gas interface, okay, where the reaction will actually take place. In CVD boundary layer, in CVD, the boundary layer refers to region of almost static gas near a surface, region of high flow near the center of tube, or wafer gas interface where a boundary condition is defined, or the gas tube interface where a boundary condition is defined. Yes, anyone? This is the place where the reaction will take place. So what it refers to? Yes, anyone? Yeah, Maya Manoj, are you there?
See, sir, whatever reaction.
Yes. Yes, what is the answer you are saying?
See, sir. See,
B,
wrapper
C.
care.
Yeah. Any other answer? Yeah, Maya Manoj, you were also saying something. Your voice is not clear. Can you speak louder? I cannot hear. Okay, fine. Try to like have a clear voice. Your voice is not audible. Anyway, so it is the reason of almost static gases near a surface where the boundary boundary layer refers to. Uh, Just a minute. Let me confirm this. Yeah. Okay. So let's come to the next question where we have state whether this is true or false. The most reliable way to obtain high growth rate is to increase partial pressure of precursors. True or false? We want to increase the growth rate. So should we increase the partial pressure of the precursor? Is it true or false? Yes, anyone? So yes, yes, continue.
I'm thinking true, sir. I don't like that. Like we have different pressures. You said earlier with the pressure rates,
Yeah.
it
If we
changes
have more
something.
if we have more molecules of reactants available, the growth rate will increase or decrease
It increases, right?
with increase.
More.
So it should be true, right? That if we have higher partial pressure, there will be more number of reactants available, and as such, we will get higher growth rate. Fine. Okay. Now let's have to sorry. Let's come to this question where it talks about quality of epitaxy. Which temperature and growth rate conditions given? See this. Okay. Both of these images are 4x, 400x multiplied. Okay. So which of these two? One is silicon CVD at 1175 degrees Celsius and another is 895 degrees Celsius. Okay. This is taken from a old image 1961. Okay. Which of these will give better probability of epitaxial, that is fully oriented and lattice matched with the substrate formation of silicon? A, that is a higher growth rate and or lower temperature. Nucleation rate is high and surface diffusion is low, enabling epitaxy growth on a crystalline silicon substrate. Second is at higher temperature or low growth rate. Nucleation rate is low and surface diffusion is high. This enables epitaxial growth of crystalline silicon substrate. A is where we have higher growth rate and low temperature. Okay. In this case, uh, it is said nucleation rate is high and surface diffusion is low. This enables epitaxy on the crystalline silicon substrate. Second condition is at higher temperature or at lower growth rate, like higher temperature and lower growth rate. That means the rate of growth is low, but at high temperature. Nucleation rate is low. That means the species are forming slowly and surface diffusion is high. That enables the epitaxy on the crystalline silicon substrate. So, which of these cases will give better chance of epitaxy? That means growth of fully oriented silicon, like whatever silicon is on the substrate, the other silicon will align to it. Yes. Any answers to this? Yes. Any answers? Anyone? Okay. So, as we have seen, just try to revise. Anyway, I will be putting the slides now. We have seen that when we have lower growth rate, that is the nucleation is slow. That is the silicon is being made slowly, and then at higher temperature it will try to align to the crystal. So the condition for which we will get better probability of epitaxy is at higher temperature and low growth rate. Okay, and from the image also you can see that in this condition, like this is quite uniform, whereas at 95 degrees Celsius we are getting some polycrystalline or amorphous kind of silicon. What are the levers to control Gibbs free energy for a reaction? For a reaction, what are the things that will determine the Gibbs free energy? Temperature, flow rate, partial pressure, or all of these? Anyone? Yes. Anyone with answer for this? What are the factors that will determine the Gibbs free energy, that is delta G, for a reaction? Yes.
D, sir.
B. Okay. Yes. Yes. Maya Manoj. Speak a bit louder. I am not able to hear your voice.
So temperature is
Temperature A. Yes. Any other answers? Yes.
All of them, sir. D, sir. D. I'm saying D, sir.
D. Okay. All of the above. Yes. Temperature certainly will have a role. Very true. Because temperature is actually delta H, that is the heat that we are providing, that contributes to the energy. Flow rate. Why flow rate? Because that will determine how much species can reach the um, actual place of reaction where the reaction optimal conditions are there. Then third is partial pressure also. Why partial pressure? Because that will determine the amount of diffusion. So all these are the factors responsible for like that can be used to control the Gibbs free energy. So changing any of these parameters will actually change the delta G for the reaction, that is the probability of taking the for the reaction to happen, as well as the rate of the reaction. The energy of the reaction will change. So now let's come to problem 6. Which among the following states the feature of a hot walled CVD? We have seen about two kind of CVD, that is cold walled and hot walled. Okay. Uniform temperature and low precursor consumption, uniform temperature and fast temperature ramp rates, high precursor consumption and slow temperature ramp rate, non-uniform temperature and fast temperature ramp rates. Which is the feature of a hot walled CVD? Anyone? Yes. Yes. When we are talking about hot walled CVD, one thing is sure, it will have a non-uniform temperature or a uniform temperature. A uniform temperature. So anyway, C and D are gone. We have A and B. Now there are two. Uniform temperature is confirmed, right? Now there is low precursor consumption or fast temperature ramp rates. Which of these is correct? Yes, anyone? Hariji? Hello? Yes. Which of this will be correct? Even if we go by this, like weeding out one thing, we have seen that when we have the hot walled CVD, everything is hot. So reactions will take place at all the positions. So the precursor consumption will be high. There are fast temperature ramp rates because if you try to increase the temperature, it will increase a lot, like very fastly increase, as well as since we have a large area, it will cool down also. Like the fluctuations are very high, but we have seen that small fluctuations will not affect our uh, deposition in case of hot walled CVD. So answer B should be the correct. No? Okay, yes, yes. This one has not given the temperature. Fast ramp. Okay, fast ramp rate is for this wafers. Yes. So in the C option, there is no talk of the temperature itself. Okay. So we have seen that it should be high precursor consumption. So high precursor consumption is C, and the temperature ramp rate is slow, like going up and down. That is not very easy in case of hot walled CVD. Whereas if we have a wafer which is singly heated, that will be giving the there we can easily ramp the temperature high and low compared to hot walled CVD. It but along with this, it has uniform temperature. So what will be the correct answer then? Yes. Anyone? It is high precursor consumption, since we have seen that since everything is heated, it will be consuming a lot. Along with this, it will have a uniform temperature and ramp rate will be slow. That is, if we want to, like suppose we have at 750 degrees Celsius and we are trying to go to 700 degrees Celsius. We set it, it will cool down slowly because everything is hot. If we want to go to 800 degrees Celsius, the whole thing has to increase the temperature instead of small area. In this case also the temperature ramp rate will be slower compared to a small area that has to be heated, and that can be done using small amount of energy or small amount of heaters. Okay. Yes. Any other questions related to the topics we have covered? Yes. Anyone? Yes. So next topic, like next week topic is physical vapor deposition. That is again the part of additive processing. Okay. So thank you. See you all in the next class. Thank you.